Okay, so our third final video for section 3.1, just to show where we left off here. We did these different compound interest problems. The first one, we had interest compounded annually. Second one, we had interest compounded quarterly. And the third one, we had interest compounded monthly. So to follow up on that, I want to give a question here. These three problems, these three scenarios all involve starting dollar of $500 and an annual interest rate of 12%. What's being changed, however, is how we're compounding it. So the first one, we're going to compound annually. The second one gets compounded quarterly. The third one gets compounded monthly. So the question is, which one of these will grow the fastest? Which one will grow the slowest? Feel free to pause the video and resume after you have an answer. What we're going to do to determine this is we're going to go ahead and just figure out what these would equal. Well, if I start with $500, increase at 12% annual interest compounded once a year, that means once a year you do get 12%. So times 1.12 to the fifth power. So I'll type that in. 500 times 1.12 to the power of 5. This becomes $881.17. A little side note here about why multiplying by 1.12 does in fact increase something by 12%. What a lot of people like to do is they say, well, if I want to take X and I want to increase it by 12%, a lot of people like to multiply by 0.12 and then add that to the original X. That's two steps, whereas ours does it in one step. They're the same things, and I want to demonstrate that by factoring out the X. And now add like terms, and I get X times 1.12. So we'll see that multiplying by 1.12 does, in fact, increase by 12%. In a similar way, this second one here, this is $500, 12% annual interest, but we're compounding 4 times a year, every quarter, every 3 months. So I take 12%, I divide it by 4 because it's quarterly, and I get 3%. And I'm going to do this for 5 years. Well, if I do it quarterly for 5 years, 4 times a year for 5 years makes a total of 20 times. So 500 times 1.03 to the power of 20 is a little bit higher, $903.06. The last of the three here, this is $500, 12% annual interest, but we're going to compound monthly, which means 12 times a year. So I have to take my 12% and I have to divide it by 12. Well, that's 1%. So 1.01 monthly for 5 years. 12 times a year for 5 years is going to be a total of 60 times. So I take 500 times 1.01 to the power of 60, and I get $908.35. So we'll see that the more we compound, the faster it will grow. So the fastest of these three, the fastest growth would be the monthly compounded. The slowest one was going to be the one that we compound the least number of times for the year, which is annually. So that's our slowest. Now there are other compounding periods. We can do daily, we can do hourly, we can do weekly, whatever it may be. We just have to divide the percentage rate by the appropriate number. Now our book gives us this format for compound interest. You'll find this, A stands for the balance after T years, P standing for the initial payment, R standing for the annual rate written as a decimal, N standing for the number of compounding periods per year, and T standing for the number of years. But this is exactly what we're doing on the problems that we had. For instance, when the rate was 12% compounded quarterly, then right here, I took 12% and I divided it by 4 to get 3%, which was made into a decimal 0.03. So I was multiplying by 1.03. Up here in the exponent, I'm taking the number of compounding periods. So for quarterly, that's 4. times the number of years, t. So this is exactly what we're doing on these problems. So I want you to understand that formula when you look at it. Now the last example involving compound interest is continuous growth. And so here's a formula. When it's compounded continuously, that means more than every second, more than every fraction of a second, it's continuous. So mathematicians have given us a formula here for how to do that. It's the principal times the e value. It's not a variable. That is the number e right here. And to the power of the interest rate times the number of years. And here I've given an example of how this works. $12,000 invested at 3% annual interest compounded continuously. We plug it in just like we've got here. 12,000 is the original. E is the number E. 0.03 is the interest rate. And 4 is the number of years. So how I type that in, just to demonstrate this for you, is I'm going to type in 12,000. Then I'm going to press second natural log to get e to the power of, and in that parentheses I'm going to put 0.03 times 4. Got an extra decimal there. Let me get rid of that. And that's how we get $13,529.96. Now there's actually, later on we'll go over more of this, more of the theory behind why that formula works. For right now, it's just important that you know how to use that. So I like to think of the exponential relationship in two basic ways. There's growth and there's decay. The number that we're multiplying by over and over, the b, this is what determines it. If we multiply by a number bigger than 1, like 1.1, 1.4, the number 2, the number 3, whatever it is, if it's bigger than 1, and you multiply by it repeatedly, which is what this says you're doing, you're taking it to a power, so you're multiplying b times itself over and over. Well, if b is bigger than 1, you're going to have growth. If b is a fraction between 0 and 1, you're going to have decay. So we saw this on the previous sheets. 2,000 times 1.05 to the 7th power. I know that's here somewhere. I had it up. I could have sworn we had a problem like that here somewhere. Well, it's up there somewhere. So anyways, 2,000 times 1.05 to the 7th power. This would be an example of, say, $2,000 invested at 5% annual interest compounded annually. This is exactly what you would do if you were trying to project 7 years out in the future. So when I type in 2,000 times this doesn't want to work. Okay, we'll go without it. I'll do it on my calculator, but 2,000 times 1.05 to the 7th power, you'll see that it becomes $2,814.20. Now, since 2,000 got changed into something bigger, this demonstrates growth. On the other hand, say that you made a bad investment, and let's say every month you've lost half of your dollar value, and that continued for a pattern of 7 months. What would you have left after 7 months? Well, you take half of it 7 times, it would look like this. Notice if you type this in, you get $15.63. The $2,000 became much smaller, so this is decay. And what's driving it is the number that we're multiplying by over and over. It's either bigger than 1, or it's a fraction between 0 and 1, and that's what constitutes growth and decay. So an example of decay, a particular radioactive material has a half-life of 38 years. Here's an expression that's going to give us the quantity of the material, Y, that remains after X number of years. So the first question here, what does the formula say is the beginning or the initial amount? Well, just like back in our previous problems, here I started with an initial value of 500. Well, along the same thought process, this starts at 20, whatever they are, 20 units. Now, why is this the equation? Well, let me talk about the half-life here. This says this is how much of the stuff is going to be left after this many years. So we're saying the half-life is 38 years here. One way to think about it would be to say, all right, what does the y have to be for this to become half of what it started as? Well, it would have to become 10 if it started at 20, and we took half of it for a number of times. Now let's talk about that x over 38 here. If I solve this equation, I try to get, let's say, x by itself, I would divide both sides by 20. That would give me 10 over 20, which would be a half, equals, on the right side, I have 1/2 to the power of x over 38. Well, this is on the left, the first power. So you'll see that x over 38 has to equal 1. The only way that's possible is if this top number is, in fact, 38. So it works. This tells us that after 38 years, you will have exactly 10 when you started with 20. So the formula does, in fact, work. So use that formula to calculate the quantity that will remain after 30 years. So what we'll do here is we're going to say, all right, after 30 years, starting at 20, 1/2 to the power of 30 divided by 38. I want to give the calculator a second try here, see if it's going to work for me. And it is not. We're going to have to do this on... So just use your calculator. If you type in 20 times parentheses 1/2 to the power of, now put the power inside of a parentheses 2, we have 30 divided by 38. And what I come up with is 11.57 about. And that should make sense because we're not quite at the half-life. Half-life would be 38 years. We're only 30 years into it. So it makes sense that it did not yet become 10. It started at 20. Half-life would be 10, but right now it's only gone down to 11.57. So that's how we use the decay formula. And what we have here, a few problems for you to try in this section 3.1. We will shoot for these in the next couple days. I'd like to get these questions all wrapped up and move on to the next thing.